everybody. Okay, I'm going to put got it. It's my pleasure to introduce Ron Hugo. He came in at very short notice because our scheduled speaker wasn't able to make it tonight, so we've got a double header. Now, Ron is currently a professor of mechanical engineering at the Schulich School of Engineering at the University of Calgary, and he also does double duty as the director of the Pipeline Engineering Centre, where he's been from 2008. And so Ron studied at the University of Calgary and then graduated there before going to take his master's and his PhD at the University of Notre Dame. He then worked in the lab, high altitude lab in Albuquerque, New Mexico, before returning to the University of Calgary. So without taking any further time up, Ron, the floor is all yours, and thanks again for stepping in at very short notice.
It's my pleasure. Thank you, Alan. And thank you for inviting me to give a talk. Let me just get the share screen going here. And as Alan knows, I always like to talk about pipelines. So, and I will try to keep it on time. And can everybody see the screen?
Yes,
okay,
I can.
Good. Thank you. So the title of the talk is Pipeline Systems and the Triple Helix. So I'm not really going to go into a lot of detail about economic, social, and environmental, but it does touch on pipeline systems, and consequently that's why I think it's somewhat important to discuss it a little bit as a preamble, describing where the research direction is within the Pipeline Engineering Center within the Schulich School of Engineering at the University of Calgary. So if you look back at the evolution of society, there have been a couple of things that have been very instrumental in terms of that evolution, and two of those have been potable water as well as energy. And we can look at a number of different civilizations that developed as a result of the benefit of pipelines. And one of the oldest pipelines is the Aqua Appia, and that was built by the Romans, and it was in 312 BC. And what it enabled was fresh water to be brought into ancient Rome. So there's the Colosseum, and then there's a very large aqueduct that comes through. But the water was brought into the cattle market, which is right up in this area here. And you can actually still go there today and see the area where they were bringing that water. So they brought in fresh water, and that enabled Rome to grow into the largest city at the time, or in human history to that point. And part of it was the fact that they had good water and they also had good sanitation. Now, flash forward a couple hundred years and we get to ancient China, and the ancient Chinese, they needed salt. They were using salt for preserving food and for many other purposes for cooking. And the place where they were getting the salt from was from salt brine. And the process that they used in order to boil off the water and have just salt at the end, was using natural gas or methane that was coming out of the ground. So they were using bamboo pipelines to route both the natural gas as well as the salt water. And it was a very, very big operation. And that enabled their civilization to advance through the use of these round conduits that we today call pipelines. Now, going even further forward in time, and we look at the evolution and the development of Canada, and one of the things that enabled the development of Canada was the Homestead Act, and that was whereby people came out and they were given a quarter section of land, and they had to develop it within a certain amount of time. And if they were able to turn it into land that was cultivated and produced, they were then given that land through the Homestead Act. And the picture in the upper middle there, that's actually Calgary, and I think it was taken in 1880. And so that's the rail station of the Canadian Pacific Railroad, which is down by Fort Calgary today. So if we look at the gas distribution system within Alberta, it actually occurred in two different waves. One of them was occurring in around 1912, and that was with the discovery near Bow Island, which is near Medicine Hat. And that discovery came as CPR was coming through. They were looking for water for their steam locomotives, and they discovered gas as a result of that. And then individuals went back and they produced that field, but it took 86 days to build a pipeline from Bow Island to Lethbridge and then to Calgary. And so Calgary received the first natural gas in 1912, and it took about a decade later for Edmonton to receive the natural gas, and that came from Viking, Alberta. And the reason was for the delay was because World War I occurred in the interim there, and that delayed the development of the pipeline going into Edmonton. And this is the distribution systems that we currently have, liquid and gas distribution systems across, or transmission, I should say, across North America. And obviously there are distribution systems that branch out even further. And so the pipeline network is very, very massive, many, many pipelines servicing a wide range of both industry as well as people. And then on top of that, there is water distribution and transmission as well that I'm not capturing here. So now the thing about the interaction between environment and society and economic, it have to realize that we now live in what they call a VUCA world. And I'm not sure how many of you have heard the acronym, but VUCA stands for volatile, uncertain, complex, and ambiguous. And so we have a lot of different things pulling on systems, and it requires engineers to navigate this space as they learn to live and operate in this VUCA world. And we had an election in the US yesterday, and there were a couple of opposing views that were being presented. We have the one on the left, which is Donald Trump's view, and then we have the one on the right, which is Joe Biden's view. Now, Donald Trump was well known for saying that global warming is an expensive hoax. And the thing that we can say is that climate change, or global warming, whatever you want to call it, it is not a hoax. Now, when we look at Joe Biden's comment, now he didn't actually make this comment, but it's along the lines of the things that you'll hear from Biden. People are saying to stop climate change. And I just want to make the comment that both of these statements bother me somewhat because they're inaccurate. And when people say stop climate change, that's not really an accurate statement either. And we can reduce the effects of what we're doing, but climate change cannot be stopped. And so when we're looking at systems that we're developing, we need to realize that climate change is an ongoing process, and it will be impacting our infrastructure that we build as design and build as engineers, and pipelines are certainly within that. So I'm just going to talk a little bit about climate change, just 2 slides here, but the main thing that we hear discussed with climate change is the greenhouse gas forcing, anthropogenic greenhouse gases, and that is the part that we do have control over. However, we can't neglect the fact that there are other forces that also lead to climate change, and that is the orbital forcing side. And I point out Milankovitch. Milankovitch was a civil engineer, obtained his PhD from, I believe it was the University of Vienna in 1920. And he got in an argument with one of his colleagues about what the source of the glacial interglacial was, and whether or not it was solar radiation having an impact on it. And so he was a brilliant mathematician, did all kinds of calculations with orbital dynamics, but he came up with a theory saying that one of the main drivers of the glacial interglacial was due to this orbital forcing, which ultimately is due to the obliquity, the eccentricity, and the precession of the Earth's orbit. And so when you look at climate change, really it is a boundary condition problem. The Earth is just a thermal fluid system. You change the boundary conditions, you affect the way that it behaves, the average temperatures. So what are we doing about it? Well, we're using technology to reduce the part that we can control, which is the greenhouse gas forcing. And so this is a slide showing some of the things that have come out of the UN and looking how we're going to get to net zero by 2050. And some of the things that we're looking at replacing traditional carbon-based fuel sources and supplementing them with be it renewable electricity or hydrogen generated from that renewable electricity. And in order to get there, we also have this blue part of the curve down here, and that's the part involving carbon capture and storage. And I went to a talk. It was probably about a year and a half ago. It was a fellow from somewhere in the US. I don't know if it's UPenn or something like that. But the thing that he was saying was that if you look at by 2050, this amount of CO2 here is the equivalent mass to the total amount of oil and natural gas that is transported today. And so if we are to get to net zero by 2050, we need to ramp this up. So we're going to be transporting a lot of CO2 around. And how are we going to be transporting it? Well, one of the ways is going to be through pipelines as well. So anyways, what we're doing is we're using technology to address the greenhouse gas forcing. And what we're seeing is a transition from natural gas and oil. Hydrogen is being proposed as one of the candidates that we can use as part of energy transition, which I'll talk a little bit more in the next slide. So this is one of the visions for energy transition, and what it involves is moving off of our carbon-based fuels, but replacing it with other sorts of gaseous and liquid fuels, and ranging from hydrogen to synthetic fuels, biofuels, ammonia. Ammonia typically, if you're going to be shipping this energy in liquid form from one continent to another by ship, but there may be some transported within the continent as well, and certainly a lot of CO2. As I showed in the last slide, we will be shipping more and more CO2 for various purposes, and so pipelines will need to be able to handle that as well. So that's the part that we can control. Now, I want to come back to this. This is a very busy slide, and I apologize for that, but this is the part that we cannot control. And what you're looking at here is Epica Dome C historical temperature data. Epica Dome C is one of the ice core sampling projects in Antarctica. It's the European Project in Ice Core. I don't know what the acronym exactly stands for. But they're actually drilling another ice core right now because they're trying to get higher resolution data. It turns out that if you go from 500,000 years to about 1 million years back, the frequency of the glacial interglacial was around 40 to 50,000 years. And for some reason, we don't know why, but about 500,000 years ago, we went into a cycle where it was around 100,000 years for the glacial to interglacial. And so what you're looking at in this plot, in the upper one, what I did is I downloaded the Epica Dome C data and processed it. And I was just curious to see if our current cycle, so this is when we were in the glacial, we hit what they call the termination. So the termination of the glacial, we have a younger Dryas event. That's when a bunch of fresh water built up and it dumped into the ocean and sent us back into a bit of a mini ice age. And then we came up and we kind of came into this stable zone. So this is stable temperature time. The future is to the left. And this is where we are right now. You can see the temperatures increasing, which is causing a lot of concern, rightly so for a lot of people. But there are papers that appear in the literature where people have commented that our current cycle appears to be very similar to the one that occurred in termination 5, which was about 450,000 years ago. They were in the glacial, they hit the termination, they had a younger Dryas event, they hit this stable period, and then they started to warm. What is the cause of that warming that occurred back here when there was no anthropogenic greenhouse gas? It's hard to say. Was it because of all the ice had eventually melted, the continental ice, and the Earth naturally warmed up? Was it because methane was emitting into the atmosphere, causing more natural greenhouse warming? It's hard to say what exactly caused it. But then eventually they went back into the glacial. The thing to note, however, is that if you compare these two cycles, we kind of do seem to be following this path fairly well. I have had discussions with some of my colleagues about this, and they said the biggest difference, however, is the rate at which we are warming versus the rate at which they warmed in previous cycles. However, what this does tell us, if we use this data as a way to be able to predict future climate, it basically is not a very good story for us, because what it's saying is that we're going to warm, and it's going to warm. This is in Antarctica. It was about 3 degrees Celsius above the pre-industrial, so the Holocene. So we're probably about a third of the way there, following if we use this as a predictive thing. So what does that mean for infrastructure and for engineers? Well, one thing for certain is it's going to introduce a lot more liquid, a lot more water into the Earth. So we will have water vapor in the atmosphere, and the oceans will rise. We'll have increased flooding. And so our infrastructure is going to have to deal with a lot more increased flooding. And here I have a picture of the flooding that occurred last November near Vancouver in the Sumas Valley. And the Trans Mountain Pipeline actually makes its way right under where this area was flooded. Now, luckily, Trans Mountain is a liquid line, and so it stays in the ground. But had it been a gas line, it would be possible for it to pop up and out of the ground, which then results in undue stress on the pipeline, creating threats and concerns. And there were also regions where there was significant washout of the Trans Mountain, and that's why it was shut down for a fairly extended period of time. So what are we doing in order to address this? Well, we're looking at pipeline threat detection research, and that's what I want to now spend a bit of time talking about. We're looking at many different ways of being able to measure the state of the pipeline, and to be able to determine whether or not it's in a scenario where there could be problems arising. Ideally, being able to determine those concerns before you have an incident, before you have a loss of fluid event. And so this is a slide that I show. Nigel is going to recognize the image on the left. That's the CCIT high bay, and the beautiful cinder block wall I believe Nigel designed. But what is notable about this is that we buried a pipe in this soil. It was compacted, and then we were circulating fluid through it, and we were measuring vibrational information. And so one of the experiments that we were doing here was external disturbance identification. Could we distinguish different types of external disturbances based on the sensors that we had on the pipeline? And so on the right, you can see some of the data streams that we collected. So no disturbance, drilling near a pipe, walking near the pipeline. We had running, we had all different types of activities, but we collected enormous amounts of data. And then what we did is we used artificial intelligence, machine learning approaches. And this is where the trick in all of these things is. You have to process the data in the right way. And so that's where we spend the majority of our time, is understanding the best way to process that data. But when we do that, we're then able to determine the external threat fairly accurately. And we're using triaxial accelerometers in the measurements that we're using. Different signal conditioning approaches result in better results there. But we're able to detect all of the different disturbances, and not only know that there's a disturbance there, but we're also able to identify what type of disturbance it is. So that's one of the things that we've been working on. And other things that we've been working on is trying to understand what are the physical signatures associated with a leak event. And so what you're seeing in these images here are high-speed video along with data that we've been collecting on the pipeline for different types of leak scenarios. And you can see each different leak has a fairly different characteristic. The other thing notable about this slide is this demonstrates the way that a lot of researchers do leak investigation, including us. What we usually do is we weld some kind of nipple or a valve onto the side of the pipe, and we open it up, and that is what we call a leak, which in a way isn't great, because it's not the real world type of boundary condition that you would have in a leak event. So common laboratory leak detection investigations involve a leak from a pressurized pipe. Sometimes there's not even a bulk flow within the pipe. It's just a pressurized pipe with no bulk flow going through it. And the leak is oftentimes simulated with a valve on the pipe wall. which is not a very good boundary condition. It's far from reality of what you would have in an actual leak event. So when you look in a lot of the literature of laboratory leak investigations versus real world leak investigations, quite often the laboratory investigations involve a bunch of valves placed on the pipe, and then they'll open them and they'll close them, and that's how they determine what the signature is from the leak. But in reality, we know leaks are far from that. And on the right, we see different types of leak events. You can have external corrosion, you can have internal corrosion, you can have cracking. They could be axial, they could be circumferential. And so the geometry of a leak is much more complicated than what we normally are simulating in our laboratory investigations. And so what we ask is there a better way that we can study leaks, ideally by trying to replicate the morphology of what actually occurs when you have a real leak. And so some of the work that we've been doing is that the idea is on the left, you would take a cutout from a damaged section of pipe. We would then scan that and bring that into a numerical model. We would then use it to do finite element modeling. And ideally what we're trying to determine is what would be the burst pressure for the pipe due to a certain amount of damage or loss of material in the wall. And here I'm showing corrosion, but it could also be with cracking or other types of damage mechanisms. Then what we want to do, we want to be able to remove that material from the outer pipe wall. And so the device that you see on the far right, I call that the pipe CNC machine. The idea there is that what we'll do is we'll remove material from the outer pipe wall to a point where we are certain that when we put it into our flow facility and we bring up the pressure, the pipe will fail naturally. And so that's what we're focusing on. And by having a natural failure, a natural leak, we can measure then the precursors of the leak, the early leak event, and the full leak event. And so in order to do that, what we're doing is designing and building a new flow facility. It will be in what we call APRIL, the Advanced Pipeline Research and Innovation Laboratory. The unique aspect of this flow facility is, first of all, we have multiple loops or lines where we can do different investigations. We'll be able to flow liquids of various viscosities at up to about 50% operational Reynolds number that you'd find in a transmission pipeline. We'll be able to flow gas in there at about 20% of the operational Reynolds number. We'll be able to flow mixtures of gases. We can do compressed air, nitrogen, gas mixtures. That would be nitrogen and helium if we want to look at hydrogen blending as proxy gases, and operating conditions up to about 100 psi. So in this earlier slide here, when I was showing you the finite element modeling, we want to know that our pipe will fail at, let's say, 40 psi, so that we can slowly bring the pressure up when the damaged pipe section is in our flow facility, and then study the dynamics of the leak itself. And we can heat the fluid and we can cool the fluid. So we have a lot of flexibility with this flow facility, and we're hoping that it'll be operational sometime in the spring semester. So that's April. And now I want to shift gears a little bit. I did touch on blending, so hydrogen blending. Here we have nitrogen and helium because I don't want to put hydrogen in this flow facility. But in order to study hydrogen, we do have another smaller flow facility that we've been using. And this is looking at hydrogen blending scenarios for customer side piping. So there's a lot of discussion about blending hydrogen into the natural gas distribution system. And one of the things that you find when you look at this is that when you look at the gas coming into your house, for example, you can have a wide range of conditions. First of all, it depends on what the draw is on your natural gas. So if it's just your pilot light, the Reynolds number of the gas flow here is very laminar. It's around 32. Your stove, your oven, your dryer, your furnace, once you get the furnace on, you'll go up into the transitional, into the turbulent flow regime. So the flow dynamics change quite significantly based on what appliance is drawing the natural gas. The other thing is that you can have a flow scenario where you have flow. If you turn off all of your appliances, you have no flow. And so you can have a scenario where there's no flow for fairly long periods of time. You can have horizontal flow, you can have vertical flow. And in terms of the Reynolds number, the flow could be laminar, it could be transitional, it could be turbulent. The other thing that we should say is natural gas, the density is around 0.7. And if you look at hydrogen, the density is much, much lower, 0.08. So we have a scenario where we can have stratified flow depending upon the Reynolds number at which we're flowing at, which all introduces interesting dynamics into what really is going on within the pipe. So in order to investigate that, what we've done is we built another flow facility. This is a much smaller one from the one that I showed you earlier, April. But what we can do with this facility is we can charge it with whatever kind of gases we want. And so typically what we've been investigating has been methane with hydrogen. And we look at various blends. So we'll look at 5% hydrogen, 10%, 20%. We've gone up to 30%. And we also look at proxy gases as well. Sometimes we'll look at nitrogen and helium, and they actually do a very good job of mimicking the behavior of what you would get with methane and hydrogen. So we can put whatever kind of gas we want into the system. We can do tests where we intentionally initiate a leak, not using the natural process. This is using a valve, but we can initiate a leak so that the gas comes through the system, comes up into this test section, comes back down, and comes through a pump. So it's basically a closed flow loop where the gas is circulating, 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 circulating. We can change the Reynolds number. We can stop the flow, observe what's happening with time. So how do we observe? The way that we do it is we have an optical measurement where we're transmitting down the length of the pipe. And what we do is we use a collimated helium neon laser beam. The inner diameter of the pipe is around 0.8 inches. It's a 3/4 inch black pipe that you'd find in your house. And with that, we have what's called a Shack-Hartman wavefront sensor, where we're able to measure the optical aberration on the light going through the system. When you have hydrogen with methane, there's an index of refraction mismatch, and we can pick that up. And that way we know when the hydrogen is coming through, we can understand what kind of mixture we might have. So we are able to get a quantitative measure of what's happening with the process. So what I'm going to show you now, this is a video collected after charging the system. We evacuate it entirely with the vacuum pump, and then we charge it with methane, and then we top it up with a hydrogen. And so when we top it up with hydrogen, the hydrogen goes into this area here, and it doesn't diffuse very rapidly. It actually likes to kind of sit right close to where you inject it. And then what we do is we turn on the pump. And so the video that I'm going to show you is what is collected when you look down the length of the test section once you start the pump. And so here will be the start of it. And you'll see, so the pump is on now. This is the intensity of the beam. I've sped this up. The beam disappears completely. That's the first pocket of hydrogen coming through. That's the second pass of hydrogen coming through. So the hydrogen is going all the way around our flow loop. It takes about 30 seconds for the hydrogen to make it around the flow loop once. And then as you keep going, what you'll find is the beam doesn't disappear. And that's because even though we're at a Reynolds number, a laminar Reynolds number of 650, we have around 20 elbows in this system. And so those are generating separated flow, resulting in mixing of the hydrogen and the methane. And so with each additional pass, you'll see that the optical variation is not as significant. And then eventually, if you run this long enough, you won't even be able to see a change, because then you're in the fully mixed state of the system, which incidentally is probably what you would get. Well, not probably, it is what you would get with the distribution system within the city if they were to deliver the natural gas to your house. So that is what the screenshots look like if you look at it at various points in time. But what we can do with this information is we can do quantitative analysis of it, and we can start to understand how long it takes to mix, what happens if you turn the system off for, let's say, a week, and then your furnace comes on again, what type of thing is happening within the flow. So we're able to get quantitative measures out of this data to understand what will be the character of these blends coming into your house. And so what we're looking at here, this is the time to mix. So it's the data that I just showed you in the video, and we have time in seconds, and it turns out to be an exponential process, exponential decay, essentially. Variance, this is variance of our optical measure. And so once we get down to this plateau here, we're fully mixed. In this region here, we have a lot of activity. So the hydrogen's coming through, then you get natural gas or methane, hydrogen, methane, and it pops up and down based on whether or not you're measuring just methane or if you have a pocket of hydrogen coming through. And the rate of decay, it's about a -2 slope is what we're finding. It's a power law relationship. And it takes about 10 minutes to get to the fully mixed state when we do that. So that's the initial charge in the mixing, which you probably would never find in your house if they were bringing in this type of a blend. The other thing that we can do, let's say we've mixed it, fully mixed, we turn the pump off and we let it sit for a week. And then we come back and we turn the pump on for 30 minutes and then we turn the pump off. So we perform that experiment and we look at what's happening. Now, this data might look significant in terms of, oh, there's a lot of stuff going on. You got to remember here, the variance was going up to 10. Here I'm showing variance 0.04. So very, very moderate optical activity coming through the system. But again, what we can do, we can get an understanding as to how much stratification might occur within the system if you let it sit. So what would stratification mean? Well, it might mean that the hydrogen moves to the high points within the piping that you have within your house. What is the implication of that? Well, as soon as you turn on your furnace or something like that, that gas is going to come through fairly quickly. You might have a higher concentration of hydrogen that the furnace might have to deal with. But after that, it'll go back to being a nice mix coming from the gas distribution system. So anyway, we can do a lot of investigations with this. And we just launched a 2-year project on this. It's an NSERC Alliance grant, so we're going to be able to study it in a lot more detail. The data that I'm showing you here was just collected during some investigations last summer. So coming back to the whole triple helix, energy, water, and quality of life, they are all kind of linked fairly closely together. The importance, however, is that we do need to have a stable, reliable source of energy, and pipelines are the main way that is being delivered to us, especially when you're looking at the ability to store energy, such as we would have now. A lot of the natural gas that we're using is coming from underground reservoirs where the gas is being stored, and then it is being provided to the city for when we have high demand. And so as we transition to some of these other fuel sources, we need to think about that and having ways of storing to give us the high quality of life that we've been experiencing. So with that, I'd like to acknowledge sponsors, Alberta Innovates, NSERC, Plains Midstream, who has helped us with April. CEPA, the former CEPA, has provided us with operating funding that we can maintain the things within April, and then ACO for the work with hydrogen blending. So with that, I'd like to thank you for your time. Hopefully I didn't go too far over.
Thanks very much, Ron. Hugh, do we have time for a couple of minutes for questions?
I think so. If anybody's got a question, yeah, please go ahead.
I just thought that Watson and Crick had it easy with only a double helix. Here we have a triple helix. Go ahead. Can you repeat that? Because I had difficulty hearing you. Ron, could you?
Yeah, I couldn't understand.
Go again, please.
Yeah.
Can you repeat your question? Or put your question. Kevin's got an idea here. Could you type it in the chat box? If you go to the chat box, you could type it, and then it might be easier, because sometimes these microphones aren't too good at picking up directionally. Would you mind doing that? If you go into chat. When I saw your first couple of slides, Ron, about the 12-year interval between bringing natural gas into Calgary and into Edmonton, I used to manage pipeline crews all over Alberta, and those guys north of us were a lazy bunch. So it doesn't surprise me that it took them 12 extra years to get the gas supplied.
I like looking at the old photos. This is the one from the Glenbow, and then
Right,
that's off
yeah.
of Google. It's very interesting to see where the pipelines were going. I couldn't find anything like that for the Bow Island one, though. Obviously.
Well, I don't have a photograph, but I have a doorstop that was taken from a section of that pipe.
From the Bow Island.
Yeah, old Cote, when he built it, it was cut up 100 years ago. It was cut up, and I used to use one of them as a prop to keep my door open.
And what was the integrity of it like?
Pretty good.
Really?
Oh yeah.
Oh, well, it's good without any coating or anything. Did it have a coating?
No.
Probably not.
No.
Ron, while we're waiting for somebody to put the question into the chat, can I just ask a quick question?
Absolutely.
I know in the lab it's kind of problematic to look at hydrogen, fully hydrogen concentration in the line, but could you maybe just comment about how viable that is in if we were trying to transport hydrogen to distribution centers?
Well, I mean, there are a couple of components to that. One is if you look at the work that ACO is doing up in Fort Saskatchewan, or if you look at the work that they've done in Europe, everybody mentions kind of a ceiling of about 20% hydrogen in the natural gas distribution system, and one of the main reasons for that limit comes down to the end use appliance and the ability of the burner to handle the additional hydrogen that is within the system. Once you get beyond that, then you get to retrofits of the equipment. Essentially, the burners, just like if you have a natural gas versus a propane burner in your barbecue, you have different sized jets and orifices and things like that. So that's from the end use appliance side. But on the distribution side, one of my colleagues in the Pipeline Center, Frank Cheng, does a lot of work looking at material compatibility. And it turns out that low-grade steel is actually the better type of steel to have. High-strength steel is a little bit more problematic for hydrogen diffusion, hydrogen embrittlement. And so people are looking at developing coatings, internal coatings that would be more impermeable to hydrogen diffusion. But hydrogen, it's a very small molecule, and it likes to go and find basically the grain boundaries and then kind of develop there. And you can get blistering where you get delamination within the wall, or it can lead to enhanced crack propagation. And so he's been studying those things. The other thing is that in order to deliver the same amount of energy, you need higher flow rate, because there's about a third of the energy density that you'd have with the hydrogen. So either you flow at a higher Reynolds number or at a higher pressure. And if you're going to higher pressure, that then drives the hydrogen embrittlement, hydrogen diffusion problem. So I think what will happen is we'll probably see the blending with existing systems up to probably that 20% limit. And then if you're looking at 100% hydrogen, there would be new lines built that either retrofit of existing lines, perhaps running a liner through it or putting some kind of interior coating on the pipe wall, or actually having new infrastructure built to be able to transport that. So those are kind of the phases that I think we'll be seeing. Some people have argued about the techno-economics of doing the blending, but I think what it is it's the people always talk about the supply and demand side. If you don't have the demand, you're not going to generate the supply in order to advance things, and so you need to get the ball rolling, where you start using it. That just like the announcement, I think it was just this morning, where it was it Air Liquide I can't remember the
Mhm.
one that it was up
Yes.
in Edmonton. Yeah, with the new hydrogen plant that where they're looking at generating hydrogen. I think probably a lot of that will go to Fort Saskatchewan. Some of it will probably also go into, you know, upgrading applications and things like that. But in order to move to having more hydrogen within our system, we need more places where it's being used. And so the blending actually helps advance that process.
Thanks very
Excellent.
much, Ron. I think we're probably going to have to
Okay.
draw it to a close, but you know, I really appreciate it. It's you're vying with three lovely ladies, and we've been keeping them waiting, Ron. I hope you don't mind, but
No, absolutely. I'd like to hear what they've been doing at
Okay,
iGEM.
good.
Thank you.